Now that we have a better understanding of regularization, let's take a look at what functions we can use for the regularization function itself. And these functions are often predicated on a specific realization of the hypothesis H. We want to choose one that's appropriate for the function at hand. We've already looked quite a bit at this case of uniform weight decay, right, where we just square the weight vector, sum up the components, and set a budget for it. You can see what that usually looks like. When we have a small amount of regularization too small, we're going to still overfit. But when we tune up the parameter to the right optimal setting, then we'll show that there's a dip in the expected test cost based on our validation output, and we'll be able to choose the right amount of medicine to dose our hypothesis class to get a good regularization output and generalize to good test performance. So you might be wondering why it's called weight decay in the first place. The reason why it's called weight decay is in neural network architectures, we typically have to use iterative training because there is no closed form solution to the optimization. And many times we want to regularize when we're doing the iterative steps. And we can think of this as a type of decay function on the weights themselves. We can also investigate lower order fit. What does this mean? This means that the case where we also penalize high weights, for example, x to the 10th or x to the 9th in the H10 scenario, a linear factor more than the case of lower weights. You can see here that it does work. We can see that when we tune the regularization parameter to a positive value of some small amount, we do get better test performance. But since these two scales are comparable here, it doesn't seem to work quite as well as letting the optimization take whatever weights it wants to assign to any feature of X rather than explicitly tune down higher order fits. Either way, between uniform decay and lower order fit, we're favoring a particular subset of hypothesis over others and trying to impair the ability of the hypothesis space to fit of the particular hypothesis well. Finally, we could also look at weight growth. Weight growth would be the idea that we want to set very big weights, right? Because if we set a big weight here, then its reciprocal will be small. So the budget in this case would be tied to how small the weights are. The smaller the weight, the bigger this term and the worse it gets. So this particular form of regularization is favoring weight growth. You can see that the expected test cost here goes immediately upwards, even with a regularization setting of 0. That means the optimum setting is 0 and basically turning off the regularization, saying that this regularization has no useful effect in controlling the expected test costs. So let's revisit the bias variance trade-off experiment, where we looked at varying the amount of noise and the complexity of the target function. We can see here when we have changed the amount of noise from 0 to 0.25 to 0.5 that we have in fact worse and worse expected test costs. But using regularization, we can control for how bad our test cost performance is by upping the dosage of medicine as the noise goes up. For example, when there's no noise in the data set, in other words, that we're actually measuring the Y values exactly accurately, as predicted, we might not need any regularization at all. We can just directly approach the solution for the regression. When there is some noise, then we can expect some amount of medicine to be taken. Without any regularization, we're going to horribly overfit, as you can see on this green line here. But with just a small amount of dose, we can make sure we come close to the minimum amount of expected test cost or validation cost. Of course, this goes up as we increase the noise level. Now, how does that compare in the case of deterministic noise or bias? In fact, the graph looks almost identical. You can see, again, when we have a lower order target function, we'll be able to fit the function exactly, and there's no need to introduce regularization. When we have a higher order target function, our points will vary a lot more depending on the sampling, and we'll need regularization to try to smooth things out. That, of course, holds for higher value target functions where the variance would be even more indicated by the data set that we sample from the input probability distribution. So in both cases, for stochastic noise, we have high frequency noise that nothing can be fit, and when we measure these y values again, we would get different values. But even in the case of deterministic noise, here they're going to be non-smooth with respect to the hypothesis set that we're looking at. So for example, if we're using an H2 to fit H10, all the H10 bumps, so to speak, would be non-smooth with respect to H2. And by setting a regularization constant, we're favoring those cases where our H2 is actually demanding a more smooth curve befitting of the number of data points that we sample. The idea behind regularization is to take the hypothesis space and constrain it in the direction of the target function. So if we knew the target function was of a certain class, what we'd like to do is make sure that first that the function f is still within the hypothesis space, but to discard most of the hypothesis space that doesn't seem like plausible explanations for f. Of course, this is a bit of a circular argument. Since we don't know f, we don't know the direction to constrain our regularizer. But the guiding principle behind regularization is the idea of Occam's razor, or to favor simpler hypotheses where possible. The idea is that a smoother hypothesis helps in both ways. It impairs our ability to fit high-frequency variance or noise that can come from either stochastic noise, that means actual noise in measurement, or deterministic noise, meaning problems with the representation as sampled by the data set. And we're going to sacrifice a little bit of the representation cost that we're cutting away from our hypothesis space for a large improvement on the variance. That's the whole idea of regularization. And even if we choose a bad omega, meaning our regularization function, for example, in the case on the last slide, we chose weight growth as one of the examples, we still have an idea of how to tune it using lambda as a parameter to set the amount of regularization that we're going to do. And we have an empirical way to do that we've taught you earlier in the pre-lecture of using validation, and we'll see how that works up next. In summary, we've looked at regularization. The idea, as we talked about on the last slide, is to give up modeling a particular subset of H to lower the variance error. We're going to do that by adding this augmented term, for which we have a tuning parameter, lambda, which we have chosen in such a way to be nicely proportional so that the math works out appropriately. We can think of lambda as the amount of medicine that we're going to take for the types of problems that we introduce. If we have a lot of stochastic or deterministic noise, we'll need more medicine, and it will correspond to being more aggressive with how little budget we are working with for our disk C that we saw in the beginning of the previous section. We also have to choose a particular regularization function, and it should be chosen with respect to H, whatever function that we are choosing through our learning algorithm. Many times, especially in neural networks, we'll find that a weight decay is common. This is called the L2 norm, where we just take the square of the weights and try to minimize that within some budget. And since we often don't know exactly how much regularization to use to set our lambda, we might choose it by validation.